a very long solenoid with lowercase n turns per unit length, and the current is I. So I'd like to do that one next. So this is sample number 3E. Okay, so what's a solenoid? So a solenoid is just like a slinky. So, you know, like and if you consider a length of 1 meter, which is the unit of length, then in that length of 1 meter, you're gonna have like 1, 2, 3, 4, 5, up to little n turns. So n turns in that length of 1 meter. Right, so understand what the lowercase n stands for. So you have a long solenoid, and if you consider a length of 1 meter, you're gonna have n turns. And then in the next meter of solenoid, n turns. The next meter, n turns, right? And we want to know what is the magnetic field, generated by the current I in this solenoid, constant current I.
Is n like a density of turns?
Yes.
Okay, that's a good density.
In fact, oftentimes this is not called very long, but an infinitely long, which means that the total number of turns is infinity. So you cannot specify the total number of turns if it's infinitely long. But you can still specify how many turns there are in a length of 1 meter, and how many turns there are in the next meter, and how many turns there are in the next meter. So the Amperian loop that we imagine in this problem is not straightforward. So I'm going to try to draw these turns over here, sort of like this. So it's like, the current is down this way, the current goes out, goes into the board. That's supposed to be a dot. So the current is out, goes down, goes into, then goes back up, right? Then it goes out again in the next wire. And I'm just gonna kind of draw it like this. And then the next wire, and then the next wire, and then the next wire. And so on, right? So all of these have currents in the same direction. I. It's the same current throughout, right? Okay. So I want to know what is the magnetic field inside the solenoid. We did the problem with the ring, correct? Do you remember the ring problem? If I put a ring like this, suppose this ring is just one of those rings, kind of. And suppose the current is this way, around this ring. What is the direction of the magnetic field generated over here in this region, near the center? What is the direction of the magnetic field? Out of the board, correct. So the quick trick is curl your fingers in the direction of the current, and the magnetic field is out of the board. If you don't like that, you could always use the Biot-Savart law. You could say, well, the current is to the right, so I'm going to think of the L this way, and then R hat is from the L to the field point, and the magnetic field, right? It's going to be in this direction. So what is the direction of the L to the right? Cross into R hat, which is up. Out. So the magnetic field here will be out. What if I put another ring with current like that? The magnetic field is going to be out. And what if I put another ring over here with current like that? The magnetic field is going to be out. So can you tell me what will be the direction of the magnetic field over here?
To the right.
So picture the current like this, right? Going around. So the magnetic field is going to be to the right. So the magnetic field is going to be to the right. And I want to know how big that is in magnitude, what its magnitude is. Okay? So the Amperian loop that we imagine here, remember, these Amperian loops do not exist. These are just things that we put in. The Amperian loop, these are just more terms of the solenoid. The Amperian loop that I am going to imagine, I'm going to use this green for that, is going to be something like this. So this is my Amperian loop, a rectangle. Yes? And I'm going to choose, well, this segment, I'm going to call them different segments. Like the one up here inside the solenoid, that would be segment number 1. This vertical on the right, that would be segment number 2. Over here, segment number 3. And over here, I'll call this segment number 4. And I'm choosing this ring and this Amperian loop. It's something that I imagine. What if I imagine this segment number 3? So imagine I have the solenoid over here, right? And I have this like rectangle. What if I imagine this segment, this one, 3 miles, 5 miles, 100 miles? It's something that I'm imagining, right? In other words, I'm going to make this very far. And it's so far from the solenoid that, well, what do you think is going to be the magnetic field generated by the current in the solenoid over here, 500 miles away from it? So I will say that the magnetic field here is 0. I'll approximate it as 0. Because it's very far away. Now, I write down Ampere's law. So Ampere's law will be this. Right? Now, this is the Amperian loop, the one in blue. So I have to do this integral, right? The circle means over the whole loop. And I split up this loop into 4 segments. Segment number 1, segment number 2, segment number 3, segment number 4. So I'm going to split this line integral on the left hand side into beta dl for segment number 1. Plus beta dl for segment number 2 plus beta dl for segment number 3 plus without a circle, because the segment 1 by itself is not a closed loop. Segment number 2 by itself is not a closed loop. So this will be beta dl segment number 4. And that's the entire loop. That equals mu naught I enclose. Yes? Okay. So But notice that I have dot product in there, right? So let me draw the magnetic field in the various segments. So along segment number 1, the magnetic field is this way, right? That's the magnetic field that I'm trying to find out, right? Over here, I said the magnetic field over segment number 3, the magnetic field is 0. Now remember that I said that magnetic field forms closed loops. So let's just say that this is a very long solenoid, so the edges are very far away. So this magnetic field is gonna come out, it's gonna go this way, be like this, right? And at some point it's gonna have to come out, you know, very far away, I don't know, 300 miles that way, let's if it's very, then it's gonna come back, and it's gonna be this way. And then it's gonna go in. Yes? So the magnetic field at segment number 2 is going to be to the left, and the magnetic field at segment number 4 is going to be to the left. Now, let me consider, so I have the magnetic field over the 4 segments. Let me consider next the, what am I missing? The L. What did we say is the L? The L represents what? An infinitesimal length along what?
Radius.
The what?
Along the Amperian loop.
Along the Amperian loop. So I could choose this one to the right, or I could choose it to the left. But since the magnetic field is to the right, in my picture, I'll just choose the L to be to the right. So for segment number 1, I'm going to choose the L to the right. For segment number 2, then the DL would have to be this way. For segment number 3, the L would have to be this way. And for segment number 4, the L would have to be that way. And notice that at each segment, right, or everywhere on the Amperian loop, I want the dot product. I want the dot product between the magnetic field vector and the L. So, let me know if it gets too cold. There are some people studying over there, and I know I'm loud. So, if you consider segment number 1, what is the angle between the magnetic field vector and the L? 0, right? And the cosine of 0 degrees is 1. So this integral over segment number 1 is going to survive. I want the dot product, so I'm interested in the angle, in the cosine of the angle between B and DL. For segment number 2, what is the angle between the magnetic field vector and DL?
90.
This is 90 degrees, right? So for segment number 2, the angle between these two vectors is 90 degrees, but remember that the cosine of 90 degrees is 0, so this is not going to contribute. For segment number 3, well, in that case, I imagined it to be so far away that the magnetic field itself is 0. You know, very far away. So this doesn't contribute. And for segment number 4, the angle between the magnetic field vector and the infinitesimal length vector is 90 degrees. So theta equals 90 degrees, and again, the cosine of 90 degrees will give me a 0, so this is out. So the only integral that will matter that contributes over here to the calculation of the magnitude of the magnetic field is the 1 over segment number 1. So this becomes the integral of B times dl times the cosine of 0 degrees, and then plus 0 plus 0 plus 0 equals mu naught. Now, what is the total current that goes through the loop in blue, through the Amperian loop? Now, I forgot to say that I'm going to imagine this length of this Amperian loop to be L, although for segment number 1. I can imagine any length, right? In fact, it doesn't even exist. And that L has to drop out. So what is the total current going through this length, L? What's the total current going through it?
I times N times L.
So I, that's the current in every wire, times what?
The number of wires N.
The number of wires per unit length
Ah,
times that length.
times L.
Right? Because this is the number of wires per unit length, and then I multiply by the length that I'm considering. And each wire has a current I in it. And it's only this one that matters, right? This is into. In this picture over here will be 1, 2, 3, 4, 5, 6, 7, 8 times I. But you have a lot of this, right? Length L. In general, it would be given by that. Now the cosine of 0 degrees is 1. The magnetic field, I'm gonna take it to be, along that length. So I'm gonna take this outside, so this becomes B, and then I have the integral of the L over segment number 1. Times 1, right? And that equals mu naught I N L. Now, what is this? What is the sum of the DLs over segment number 1? Just the capital L. So what we have then is that the strength of the magnetic field inside the solenoid times L equals mu naught I N L. And it doesn't matter how long I imagine the Amperian loop to be. It shouldn't be there in my answer, because it's something that I'm imagining. I mean, if someone else imagines a longer Amperian loop, they should not get a different answer. We should all get the same answer. So the result is that the magnetic field inside the solenoid is mu naught Ni. It's usually how it's written. Mu naught Ni. And what else do you notice? It's along the axis of the solenoid, so this is axial. Instead of being circumferential, this is axial. And what else do you notice? It doesn't matter where you are inside the solenoid, so it's uniform. Do you remember? The magnetic field is uniform. It has the same magnitude and direction everywhere inside the solenoid, if it's a very long solenoid, right? An infinitely long solenoid. Do you remember of a case when we saw for an electric field that was uniform over some region of space? Not necessarily 0, but something but uniform. A set of parallel plates. It was 0 here. It was 0 here, but here it was like that, and of the same magnitude everywhere, so it was uniform. That one gave us a uniform electric field in the region of space between the plates. Large, infinitely large plates, or very, very large plates. Well, the geometry, the situation that will give you a uniform magnetic field in space, right, pointing in the same direction and of the same magnitude, is an infinitely long solenoid. Inside the solenoid, it's along the axis. So I wanted to do this example because, if somebody asks you, what is the magnetic field inside a solenoid? It's difficult to even come up with this rectangle, and then you have to make this one conveniently far away so that it's out of the picture, and then you can just solve for that, right? So I wanted to do that on the board. So we're not going to do this problem again. I'm not going to ask you in an exam to do that, but be familiar with this, know how to use it, depending on the problem and so on. Just remember it's along the axis. And if the current in the solenoid is like this, right, out the top into the bottom, it's going to be to the right. If you flip the direction of the current, if you reverse the direction of the current, then it will go in at the top, out of the bottom, and the magnetic field is going to be to the left, inside the solenoid. So I've done, I think, oh. Sorry about the stuff over here. They also there see stuff that says OCC. So we talked about cross products. We talked about the Biot-Savart law. We did the calculation of the magnetic field generated by a very long straight wire. Well, not very long, a wire of length twice L, I called it. Distance Z, I think I called it, above the midpoint, above the center. We also did the infinitely long or very, very long straight wire. We did the ring, and we found the magnetic field on somewhere on the axis of the ring with current I in it at a distance x from the center of the ring. And then Ampere's law, we did the toroid, we did the solenoid, which is here, we did some wires. So that's it for this chapter. Today is Wednesday, right? So a good day for exam number 2 will be next Wednesday. Do you want a quiz on chapter 28 next Monday? That'll force you to do 28. And then it'll be a matter of just reviewing for the test. And on that Monday, you could also ask me all the questions you may have, and then next Wednesday.
Before the quiz, are you gonna release any of the homework for Coral on chapter 23?
I should write myself a note. I should. I'll assign a few, 5 or something like that. If not, look at the homework for which, well, the problems for which I posted out solutions. A lot of them in there. But yeah, I have to look into that. So, will that be quiz number 4 only? Oh, wow. Okay, so how about quiz number 4 next Monday? And then on chapter 28, well, next Monday, on chapter 28, and then exam number 2 next Wednesday. On chapters 24, 25. So I'm going to put a problem. 24 is on capacitors. I'm going to put a problem with a circuit with capacitors, find the charge in every capacitor, that sort of thing. 25 and 26, I'm going to put a problem where you can use Kirchhoff's laws, or maybe in series, in parallel, a circuit with a DC battery and a whole bunch of resistors. And then 28, you know, maybe I'll definitely put an Ampere's law problem, and maybe I'll put one where you have to use the Biot-Savart law, something relatively simple that you don't end up with a complicated integral or anything like that.
So, one problem 24, one problem 25, 26, and two from 28.
Yeah, I think the first exam was out of 20, was it out of 60 or 75 points?
60.
60, so I can put 4 problems, 15 points each. Or no, you don't like that?
That's good.